Hi, today we are looking at section 8.3, which deals with radian measure. So we will start dealing with angles and radians instead of degrees, and we'll go through our conversion factors to switch between the two, as well as solve some questions in radians. So first thing we'll talk about is our arc length and angles in radians. So essentially, if we have a central angle of 1 radian, what that means is our radius is going to be the exact same length as our arc. Now, if those are not the same, our angle here will determine this arc length. So that gives us this equation here, in which our arc length is equal to our angle in radians times our radius. Now, one key thing is our angle, if it's in radians, doesn't have a symbol with it. So if you see a symbol with an angle, it's going to be in degrees. If there's no symbol with it, it's going to be your angle in radians. Now, we can utilize this formula to figure out where we have different radians on the circle. So just like with degrees, we start out at 0 here. Now, from math in earlier grades, we know that going all the way around a circle, that distance known as our circumference is given by 2 pi r. So if our arc length is 2 pi r to go all the way around our circle, and we've got our arc is equal to theta r, that means that going all the way around a circle is 2 pi radians. So if we go all the way around here, that gives us 2 pi. Now, halfway around would mean that this is pi. Half of that would be pi over 2. And this would be 3 pi over 2. Now, from this, we essentially know that from here to here is pi, but that's also, if we have in degrees, is 180. So that can give us this conversion factor that 1 radian is equal to essentially 180 divided by pi. Now, if we are to change things around a bit to get an angle on its own, 1 degree is equal to pi over 180. Radians. Now, if we are going to convert to, say, radians from degrees, we'll multiply by this scale factor. If we are going 2 degrees from radians, we'll multiply by this scale factor. So in these examples, we're converting to radians. So if we're converting to radians, we're multiplying by pi and dividing by 180. So that 517 degrees works out to 9.02 radians. 240 will multiply by pi and divide by 180. And with numbers like this, where it looks like we can reduce to lower terms, we tend to reduce to lower terms instead of changing to decimals. So that'd be 4 pi over 3 radians. Same as this one, multiply by pi, divide by 180. So that'd give us 37 pi over 18, and that's negative. Okay, next example, convert the following radians 2 degrees. So we're essentially using the same scale factor except for the reciprocal of it. So we're going to multiply by 180, divide by pi. So 8 radians works out to 458 degrees. We'll multiply 4 by 180, divide by pi. And we get 229 degrees. Negative 17 times 180 divided by pi gives us negative 974 degrees. Now, just a reminder of special triangles. We have our 2 main special triangles. So we've got our 45, 45, 91, which we will want to know these angles in radians now that we're dealing with radians. So what we want to do is go 45 times pi over 180 to convert that into radians, and we'll do it as a fraction. So we won't change it to a decimal. So that gives us pi over 4. So this would be pi over 4. This is pi over 4. And just a reminder, this one's 1 square root of 2. This one we had our 30, 60, 90 triangle. So we'll want to convert each of those. And we also remembered that this was 1, 2 square root of 3. So first we'll convert 60. So we've got 60 times pi over 180. So that is pi over 3. So 60 is the same as pi over 3 radians. Next we'll convert 30. So 30 times pi over 180 gives us pi over 6. This angle is pi over 6 radians. Now, determining trig ratios for angles and radians, what we want to do is draw out our question. Once we have it drawn out and where our terminal arm is, we can find our reference angle. And then if that reference angle matches a special triangle, we'll label our sides with the sides we just went over, and then fill in our ratios. So for example, determine the value of sine of negative 13 pi over 6. So we'll draw out coordinate system, and then what I'm going to do is look at this. I can see that if I just compare the 13 and 6 and ignore the pi for now, that's going to give me a number that's greater than 2, which means we're going to go all the way around once. So what I'm going to do is rewrite this as sine of negative 12 pi over 6 minus pi over 6. Because if we add these together, we get that. So this is the same as sine of negative 2 pi minus pi over 6. So we're going around once and then an additional pi over 6, and we're doing it in a negative direction. So there would be our negative 2 pi, and then we're going an additional negative pi over 6. So our angle would be, this would be our total angle, and our terminal arm would be down here. Now, our reference angle is just going to be that pi over 6. Now, we just went over that on a previous page with our special triangles. Opposite pi over 6 is 1. Now, this is in a downward direction. That's negative 1. Adjacent to it is our square root of 3, and our hypotenuse is root 2. Now, sine of our angle is opposite over hypotenuse. So in this case, we've got sine of negative 13 pi over 6. So our opposite was negative 1 over our hypotenuse of 2. So there's our ratio for it. Next example, use your calculator to find cotangent of 12 pi over 5 to the nearest hundredth. So this one, because it says to use our calculator to find it, we aren't having to draw anything out. We just want to make sure, because this is in radians, that you have your calculator change to radian mode from degree mode. So if you have one at Texas Instruments, graphing calculators, you're just going to hit mode, and the third line down lets you switch between radians and degrees. Now, because it's a cotangent, that means that if we're calculating cotangent of 12 pi over 5, what we're really calculating is 1 over tan of 12 pi over 5. And it says the nearest hundredth. So when we enter in, we were going to round to 2 decimal places. So this gives us 0.32. Okay, next example, we're looking at a word problem. It has 2 parts. The International Space Station travels at a speed of 27,600 kilometers an hour at an altitude 400 kilometers above the Earth. The Earth has a 6,400 kilometer radius. To the nearest tenth of a radian, through what angle will it have rotated after 40 minutes? And what is the straight line distance between the points? So essentially, if let's say this is our radius, we have this arc. It looks something like this. Our radius here would be the combination of how high it is above Earth and our radius. So this is 6,800 kilometers. Now, we have our velocity and time, so we can actually figure out our arc length, because we can get our distance by taking our velocity times time. So we have 27,600 kilometers per hour times, we want this in hours, so that'd be 2/3 of an hour. Hours are going to cancel out. So that gives us 18,400 kilometers. Now we want to figure out this angle here. We have our arc length, so this is our A. We have our R, so we can use our A is equal to R theta. Now we want to get our angle, so we'll divide both sides by R. So we have 18,400 divided by 6,800, and that gives us 2.7 as our angle. So 2.7 radians. Now part B, we want the straight line distance. So we want to know this distance here. So we can utilize something from Precalculus 11, because essentially we have a non-90-degree triangle. We know 2 sides of it. We have an angle between those 2 sides, so that means we can use cosine law. So for part B, we're doing c squared equals a squared plus b squared minus 2ab cos of c. So we have essentially c is equal to a square root of 6,800 squared plus 6,800 squared minus 2 times 6,800 times 6,800 cos of 2.7, making sure our calculators are in radians, and that gives us C is equal to 13,270 kilometers.